So welcome everyone to CC Colloquium for March 10th, 2021. 1 year anniversary since we all started going virtual. So that's pretty remarkable. And I'll say no more about that other than that's pretty remarkable. Minnie and Ramona are both absent today, unfortunately, but they have no announcements. I just have one quick announcement to remind everybody that next week we have another one of our special colloquia. A couple of our postdocs will be giving presentations. Park Lloyd and Hayden Miller. So please be sure to come to next week's special CC Colloquium. And with that, I'm happy to turn it over to Evgenia to introduce our speaker.
Thanks, Ariel. Hi, everyone. Good to kind of virtually see you and feel all together again a little bit. Very much, I would like to welcome David Brain, Professor David Brain from CU Boulder, who is virtually visiting us. But we'll come back in person, I'm sure, sometime soon. He is an associate professor at LASP, which is the Laboratory for Atmospheric and Space Physics and the Department of Astrophysical and Planetary Sciences at CU Boulder. Prior to that, he was an assistant research physicist at UC Berkeley's Space Science Laboratory, and he did his PhD also at CU Boulder. So you know the place well and you're back home, so that's great. David is also a key member of the MAVEN mission to Mars, which you'll hear a bit about today. He's also, one thing that I have watched a couple of times is David Brain's excellent TED Talk from a few years back. It's a great TED Talk and I love it, and your enthusiasm totally shines through, and I'm going to paste the link into the chat. 2 million people, David, have already watched it, so what's a few more, all right? And it's called What a Planet Needs to Sustain Life. So I will paste that into the chat shortly. But today, David is going to give us a talk, which the title is, Do Habitable Worlds Require Magnetic Fields? Now, when I sent out the colloquium invitation, I heard opinions from people. I actually got votes back. So I thought it would be fun for us to vote. Because that's how we do science, by voting, to vote at the beginning of David's talk, and then he suggested we then vote again at the end and see how convincing, how right or how wrong, or a little bit right or a little bit wrong we all have been. So thank you, David, for coming. Ariel, if you could load up the poll, that would be awesome. And if everyone could take 1 second and vote, that would be great. Is everyone able to see this? Yeah, not just me. Great. We'll give it a second. Look at all that.
Votes are pouring in, so 2/3 have voted already. 3/4.
No, where's the "we have no idea" option? You have to be bold, Mike. Just pick one. Okay.
All right. Well, it's about 2/3 to 1/3. 2/3 say yes, 1/3 say no.
Okay. Well, with that in mind,
we'll see. We'll see if you reinforce that or set us straight, David.
Okay, great. Thanks so much.
Oh, I'm sorry.
Oh yeah, go ahead. Evgenia.
No, I didn't mean to interrupt.
Oh no, I just said with that in mind, I wanted to pass it off to our speaker, David Brain. Thank you so much.
Great, thanks a lot, Evgenia. And also, you should be sure to show up next week for the colloquium. I was on Park Lloyd's thesis committee, and he's great. And with the result of that poll, I think my work here is pretty much done. I can now write up my final report to NASA, and I'll just take questions from here on out. That's my plan. Okay. So this is a topic that I've been thinking about now for a couple of years, and think I'll probably continue to think about it for a few more, but hopefully this isn't a question that will linger for the entire rest of my career. I think it's something that we can actually resolve and make progress on in relatively short order, in the matter of a few years. I like big picture questions like this. Do habitable worlds require magnetic fields? And that's a short 6-word question that I think is intriguing and involves some hard and deep thinking in some places. So thanks very much for having me. I'm really appreciate the opportunity to tell you a little bit about this question that's fascinated me recently. So let's start off by me telling you what I think about when I hear this question. And you may or may not be surprised to realize or to hear that the first thing I think of when I think of magnetic fields and life are homing pigeons, which I have no direct experience with. And here's an image, I believe, from the middle of a field in the UK someplace where homing pigeon races are much more common than here in the US. And a whole bunch of homing pigeons are being released from this sort of trailer right here. And then they have to find their way to their destination. And the reason that this is the thing I think of first is because it turns out homing pigeons use Earth's magnetic field to navigate. And also, I think I've always wanted to include a slide in a talk for my field that has the title Italian Zoology of the 1970s, because it seems so random and non sequitur. But here is a journal article from 1976 about the correlation between race arrivals of homing pigeons and solar activity. And it had already been known that homing pigeons use Earth's magnetic field to navigate a little bit, but this was one of the first publications that showed that during solar activity, the success rate of homing pigeons went down. So here, Wolf numbers is some indication of solar activity on the sun. And here is the percentage of homing pigeons that arrived within the allotted time. And there are a couple of anomalous events here that I think in the paper it describes these happening during inclement weather conditions, but the rest were relatively clear conditions, and the success rate is much higher when solar activity is low, and it goes down past that. So I find this fascinating, but maybe enough about the homing pigeons already. Actually, after this slide, because I'm pretty enamored with the homing pigeons. And in putting this together, I found this website here for the RPRA. It's an acronym even. It's the Royal Pigeon Racing Association. And the Royal Pigeon Racing Association has this website that talks about race programs. And right on the front of their website is a warning about a solar flare. And so this is something that they actually keep track of when they're going to hold homing pigeon races. I was somewhat dismayed to find out that this website hadn't been updated since 2014, however. So let's move on. Okay, so with that in mind, the homing pigeons finding their way home, you know, the solar activity isn't determining whether those homing pigeons can live or die or survive. If Earth had no magnetic field, the homing pigeons would probably find some other way to navigate. So this isn't really the topic of conversation that we should be focusing on when we're trying to answer this question. So instead, let me lay out the problem a little more directly here. So there's a chain of logic that you might use to connect magnetic fields to habitability, and it involves several assumptions. So that chain is laid out here in diagram form, where each of the black arrows means requires. So life requires water in a liquid state. Water in a liquid state requires that a planet have an atmosphere. And having an atmosphere requires that a planet has a global magnetic field, at least as laid out here. But there are several assumptions that I made along the way. First of all, for this first link, I assume that life is Earth-like and that any life on another planet also requires liquid water. That's a fairly standard assumption. I'm not concerned about this one for right now. Liquid water requiring an atmosphere means that we're really talking about life on the surface of a planet, or maybe even above in the clouds, which is been a recurring topic of conversation for decades now, but recently came up again within the last year. So we're not talking about Europa or a planet with a subsurface ocean. We're talking about life that we might be able to observe on a planet remotely from far away or detect from far away that's at the surface or above. And then finally, this last link between atmosphere and global magnetic fields assumes that a global magnetic field shields the atmosphere, that it protects the atmosphere and makes that atmosphere possible. So what this means is it protects the atmosphere from escaping away to space. So confirming or disproving this last link, at least in my mind, has implications for topics related to Earth's history and Earth's future as well, maybe even Earth during geomagnetic reversals too. It also has implications for planetary topics, the co-evolution of the terrestrial planets, the three big terrestrial planets with atmospheres, Venus, Earth, and Mars. They started perhaps in relatively the same state or a much more similar state than they are today, that they had a divergent evolution. Did the magnetic field play a role in that divergent evolution? And then finally, exoplanetary topics as well, as we increasingly come to know thousands and thousands of planets orbiting other stars. Does whether or not that planet has a magnetic field play some role in whether it's retained an atmosphere and therefore liquid water is possible on the surface and even life? One last caveat on this slide, there's a brief disclaimer that I'm temporarily neglecting the influence of a magnetic field on surface radiation, except for the next slide where I'll talk about it for one slide. And I'm also neglecting the influence of a magnetic field on chemistry that can happen in the atmosphere. And it's been shown that there is a link there, that there can be a link there, especially for nitrogen and oxygen bearing compounds, for example. But I'm not going to focus on that topic. And I'm going to skim past surface radiation, except for this slide, to claim that radiation is pretty unimportant for Earth today. And you can find pie charts like this all over the internet. And here's one that I just took from the EPA. And it shows the contributions, many different contributions to the ionizing radiation environment, the ionizing radiation environment that might be harmful to life on Earth. Space background is about 5% of the total radiation environment that life on Earth is experiencing. And that space background consists of both photons and particles. So both light and things with mass. It's only the things with mass that could be influenced by a magnetic field. Life just sails right on through. So the actual influence of a magnetic field on the radiation environment on Earth's surface today should be much less than 5%. If we assume that it's some planet without civilization, then several of these wedges go away. The industrial occupation, consumer, all of the medical things go away. But even then, this wedge would maybe comprise about 10% of the total radiation at the surface of a planet. So for now, I'm going to neglect that magnetic field radiation connection at the surface and just focus on atmospheric retention. Okay, so for this next link, getting from liquid water and needing an atmosphere to retain liquid water, a phase diagram for water would be a natural thing to look at there. This is maybe one of the more complicated ones that you will come across when you type water phase diagram into Google Slides. Nevertheless, you see solid, liquid, and vapor forms of water. And as you know, we spend most of our daily experience thinking about those different phases along the temperature axis. But the pressure axis becomes important when you're comparing planets to each other as well. So we could crudely put the three big terrestrial planets on this map. And this is done very loosely and by eye, but Earth would be somewhere here at the boundary between solid and liquid with surface conditions. And of course, vapor is possible on Earth as well. Mars at much lower pressure is near the triple point of water. So liquid water is only possible at certain locations on Mars and only certain times of year. It's not long-lived or stable for long periods of time at present. If Mars had more pressure in the atmosphere, then liquid water could be more stable. And we have lots of evidence from the Martian surface that that was the case long ago, that Mars has moved on this diagram downward over time. Finally, Venus is a really tough case, at least down at the surface. Maybe up at the cloud tops, Venus moves down on this diagram as well and becomes more clement. But at the surface, you're way over here on the diagram. Venus is a rough neighborhood. Okay, so in order to have liquid water, we need to have that atmospheric pressure, and then atmospheres can escape. Atmospheres are made of individual atoms and molecules. If you give that atom or molecule enough energy, it can escape the gravitational pull of the planet. And there's a temptation to use this phrase, atmospheric escape, and assume that it refers to a single process. But there's actually a rich array of physical processes that are all captured under this umbrella term. So there are processes such as thermal escape. A collection of particles has a distribution of energies. Some of those energies are above average and may be so high that individual particles can escape the planet. Usually only important for things like hydrogen in planets in our solar system today, and only at certain planets as well. Then there are non-thermal processes, photochemical escape. Sunlight can split apart molecules like O2 molecules and give them energy in the process. And the energy that they acquire from that photochemical reaction will make it so that one of those oxygen atoms can escape away to space. The other one, of course, goes the other direction, down towards the planet. Sputtering is when something splashes into the planet, like throwing a pebble into a swimming pool. When you do that, a few droplets of water might splash out of the swimming pool. And if you do that for 4 billion years, maybe you can splash a lot of water out of the swimming pool. And then finally, ion escape, which itself is a catch-all term. Ions are given energy by electric fields. And there are 3 or 4 different electric field terms that can all provide energy to ions. But they can all end up working together as well. So these days, and I'd say within the past 10 years, the community has started to just refer to this as a single process, as opposed to referring to ion pickup and ambipolar electric fields or terms like that. We just say ion escape. This escape channel is most obviously influenced by magnetic fields, because magnetic fields tell charged particles how to move. But there may also be indirect influences of magnetic fields on some of these other processes as well. This is what happens in normal times on a planet like Mars. But then there are also extreme events that stars can send towards planets. This is a coronal mass ejection, a large density of material with a strong associated magnetic field. There can also be flares, just lots of light or photons at X-ray or extreme ultraviolet wavelengths. And then there can be solar energetic particles as well. So these are sort of extreme versions of the stellar inputs that drive escape from planets. So where does a global magnetic field influence these processes? That's sort of a major question to be asking in relation to this question. So I'll give you the answer to the question. Magnetic fields should protect atmospheres, and it's simple physics, and that's why this is the correct answer. It's because the physics are so direct. Mars lacks a global magnetic field driven by an internal dynamo. Earth has one. It has a strong intrinsic magnetosphere, whereas the magnetosphere, or the region of influence of the planet in terms of particles and fields for Mars, is much smaller, much more compact. It's an induced magnetosphere. And a magnetized planet can deflect the charged particles that are flowing from the sun, the solar wind, and it can deflect them very far away from the atmosphere. That means the solar wind never encounters the atmosphere. That means the energy from those particles isn't being used and impacting atmospheric particles. And so the atmosphere can't escape as efficiently. The solar wind can't drive that escape as directly as it can on Mars. And this is a reminder that this is the main role of a magnetic field for a question like this, is if you have a charged particle and there's no magnetic field, it's going to move in a straight line given by whatever its initial velocity is. But as soon as it moves into a region where a magnetic field exists, the particle is going to take a left turn or a right turn, depending upon whether it's charged positively or negatively. And so that's why these charged particles screaming towards Earth get deflected around the planet, because the Lorentz force from the magnetic field deflects them around. There are observations that support this idea that magnetic fields do provide shields for atmospheres. One of them, I know at least one of you here has seen already today in another talk that we were in together. There's no real x-axis on this diagram. It's a paper by Genda from Japan showing the ratio of deuterium to hydrogen in various solar system objects. And objects that are thought to represent the composition of the pre-solar nebula have a certain D to H ratio in them. So the giant planets would fall into this category. Earth has an elevated D to H ratio and carbonaceous chondrites as well. Mars, depending upon which part we're talking about, is more elevated in D to H than that. And Venus is off the charts, elevated in D to H. This ratio is important because these two species behave chemically identically. The only difference between them is their mass. And it turns out at the tops of atmospheres, the atmosphere is not well mixed there. So massive things are sinky. They kind of sink to the bottom of the upper atmosphere, and light things are floaty. They float much closer to the interface between the atmosphere and the space environment. That means that hydrogen, the light isotope, should be removed preferentially to space, leaving the atmosphere enriched in the heavy stuff. So for these objects that have large D to H ratios, that means the atmosphere is enriched in the heavy stuff, and we can infer that escape has been an important process for those planets over their lifetime. The unmagnetized planets, Venus and Mars, are elevated in their D to H relative to Earth, suggesting escape has been more important for both of those objects, which both lack a magnetic field. We also have direct observations of escaping particles from spacecraft that orbit these planets. One that you mentioned, that Evgenia mentioned at the beginning here, is MAVEN, a spacecraft that's been orbiting Mars since 2014 with the scientific goal of studying atmospheric escape processes and the reservoirs for escape and the drivers of escape and the evolution of the Martian atmosphere. We have an instrument that measures charged particles escaping from the planet. And my postdoc, Yashui Dong, did this back in 2015. And if the sun and solar wind are, sun is at the right and the solar wind is coming at Mars from the right, the colors here show you the numbers of charged particles escaping from the planet, and the lengths of the arrows show you the energies of the charged particles. And basically, we can see that there are multiple different pathways that charged particles take when they're leaving the planet Mars. And these are oxygen ions, by the way. So there's no chance that this is solar wind charged particles. This has to be coming from the planet. And there's one channel that's very energetic with long arrows. And there's another channel that's not that energetic, where particles escape down the tail away from the planet and away from the sun. But when you add all of this up and you make a best effort to extrapolate this kind of work backwards in time for Mars, the observations indicate that through this process and the other escape processes together, that Mars has lost at least half a bar of atmosphere over time, or half the thickness of Earth's atmosphere, and maybe as much as 1.5 or 2 bars of atmosphere over time, and that ion escape has been a definite and significant contribution to that overall escape. Unfortunately, the talk would be over if I didn't have this slide, but there's another answer that could also be correct, and that's that magnetic fields should not protect atmospheres. And this is unfortunately also pretty simple physics, which is why this question has come up recently in our community. The simple physics are that you don't need the particles to crash into the atmosphere in order for their energy to be transferred to the atmosphere. As a matter of fact, a magnetic field provides a means for transferring energy from charged particles to the planet through something called the Poynting flux, which is dependent upon the electric field in the plasma and things like that. However, what this means is that the magnetic field can act a bit like the sails on a ship. If the magnetic field weren't here, this little tiny planet would be subjected to this little bit of solar wind right here. But when you make a big magnetic field, suddenly it can intercept even more of the solar wind and capture more energy because of the larger cross section. that energy ultimately gets focused down the magnetic field lines into the cusps of the magnetic field, into the North Polar region and the South Polar region, the same places that we get aurora for the same reasons. And so escape from Earth has been measured coming from these regions. We've seen all of these different types of ion species escaping from Earth. It's not global escape like it is for Mars or Venus. It's coming from a much more confined region, but it's very efficient as well. So there's support for this idea that magnetic fields don't protect atmospheres. And this idea has come up in the last 10 years and started making us rethink the canonical assumption from 35 years ago that magnetic fields are shields. One of the pieces of support comes from measures of this pointing flux that I mentioned before. This is a quantity out in the solar wind before the solar wind hits Earth. And we can measure the pointing flux and compare to the escaping ion flux at the same time. So let me change the labels on this plot. And it's really energy in versus ions out. And there's a definite correlation. Earth escape cares what the solar wind is doing, suggesting that the magnetic field is at least an imperfect shield, that the information from the solar wind gets into the atmosphere and helps control escape. There's an asterisk here that I'll come back to later, maybe. Another piece of support is that for this idea that magnetic fields should not protect atmospheres comes from the surprising realization that after we sent spacecraft to all 3 planets, Earth, Venus, and Mars, and measured escape from all 3 planets, we found that the escape rate to within an order of magnitude is the same at all 3 planets. The magnetized Earth has about the same amount of escape as the unmagnetized Venus and Mars. There's a definite asterisk here. This is not an apples to apples comparison. These 3 planets are different sizes. They're in different parts of the solar system, subjected to different conditions, with different spacecraft around each and different instruments with different sensitivities and energy ranges. So there's a lot of work here to be done to be able to make this kind of statement with confidence that the escape rate is the same from all 3 planets. But it's certainly suggestive that they seem to be similar so far, and maybe the magnetic field isn't so important. So a solution, a potential solution, well, first, let's acknowledge that this is a hard question. There are a lot of different approaches that are needed, and there are a lot of different planets involved that need to be compared in order to come up with an answer. So the best solution that a group of us could think of was a multi-pronged approach that uses team science. You've perhaps heard of team science institutes, maybe one of the astrobiology institutes from NASA. The team sciences approach is also used in some subdisciplines of the NSF, for example, chemistry, sometimes as well. So a group of us proposed for a team science center from the NASA heliophysics division. And to our great delight, it was selected for 2 years of funding. So this is a kind of a different funding model. They selected 9 of these heliophysics science centers and gave us all 2 years of seed funding. And then this December, we have to re-propose a second time, incorporating 2 years of progress into our proposal, and then they will down select to 3 teams to be carried forward for more substantial funding for a 5-year period. So we're about a year and a quarter into our award right now. The name of our center is MACH, Magnetic Fields, Atmospheres, and the Connection to Habitability. When you do team science, you want to acknowledge your team, and we have a great group of heliophysicists and planetary scientists and astrophysicists, and their approach to science spans observations, big box simulations, and sort of whiteboard theory approach. So we're hoping that we have all bases covered on this team, but the team is likely to grow if we are selected for the next round. And then to advertise to you, don't worry, these 2 slides are the only advertisement, self-aggrandizing advertisement for the center. But why this might be of interest to some of you is that we have to come up with our mission statement, what we want to provide to the community. And the mission statement is here in words, but then I'll explain it in different words. So we'll construct a framework that enables the evaluation of atmospheric loss from an arbitrary rocky planet, given information about the planet and its host star. And what I might imagine there as one facet of that is some kind of web interface where anyone in the community can go and kind of dial knobs to tell us a bit about their planet, what the planet is like, what the star is like. And then under the hood of the website, we'll use the combination of results from the model, empirical results derived from observations, to provide a response, hopefully in semi-real time, about how much escape you could expect from that kind of planet. So that's our goal, is to provide something like that to the community. The last advertisement is that we're going to hold a 3-day community workshop on whether habitable worlds require magnetic fields. It will be virtual. We're not quite ready to go back in person yet, and it will be in June. And please feel free to contact me if you're interested. So let's move into the next portion here. Let me just pause for a second to get a drink and check to see how I'm doing on time, and then dive back in. So one of our approaches, and of course I started talking before I had the drink. One of our approaches is to compare Venus, Earth, and Mars in the observational track. Why is Earth just right when Venus and Mars are not just right? So what do the observations tell us so far? And I already alluded to this, that not all of the escape measurements of the 3 planets are created equal. And this is made, the same point is made in both figures. Let's start on the fun one to the left. This is a simulation of the entire inner solar system, colored by the density of the solar wind. The sun is at the center. Earth is the green dot over here. Venus is here. Mars is over here to the left. And a few relevant spacecraft that are making observations of space weather are also indicated as well. This simulation was done for a solar storm that happened in September of 2017. And you can see that density release of material from the sun as it propagates past Earth. And there are multiple releases that go and hit Venus and maybe glancing blows at Mars as well. This makes the point, I think, that Earth, Venus, and Mars are subject to different conditions, not just as a function of time, but also as a function of their distance from the sun, which is maybe better captured here in the plot to the right. So these 3 different colors are for Venus, Earth, and Mars, and they're basically contours or 2-dimensional histograms of the kind of conditions you could expect to experience at Mars, in terms of the density of the solar wind that's flowing from the sun and the velocity of the solar wind as well. So you can see the kinds of conditions we experience from Mars are not the same as the kinds of conditions that Venus experiences. Venus is closer to the sun. The density of material it encounters is higher. And so that's another reason that these comparisons are not apples to apples. But there's hope in the fact that these distributions overlap each other. So we could be selecting conditions from each of these different spacecraft missions at each of the planets and saying, for identical stellar inputs to the planets, is the escape the same from the 3 planets? There are going to be other differences as well in planetary size and composition and the energy ranges of the instruments, as I said before. So we're already getting some results back just by looking at 4 papers. And so here's a plot where I've tried to take lots of lines and just make a few blobs to guide your eye. This is the escape rate from the planet, organized by the pressure in the solar wind, how hard the solar wind is blowing. And as the solar wind pressure increases, Mars, stays roughly the same. Maybe escape goes up or down. It's kind of hard to tell. Venus only experiences strong pressure conditions, but there's a pretty clear increase in escape for Venus as solar wind pressure increases. But then Earth, the magnetized planet, has a very, very strong increase in escape, at least from the paper represented here by Audrey Schillings in our community. So there's a much larger response of the magnetized planet than there is of the unmagnetized planets. Maybe having a magnetic field enhances escape from planets. That's what this plot might suggest. However, there are more than 120 previous studies to mine for information, and a very talented undergraduate of mine who's graduating this semester has pulled together all these studies and is starting to mine them for the escape rates and the planet and what instrument was used, so we can make a more detailed version of the plot that I just showed you. Another person, whoops, that was backwards. Another person in our group has gone back and taken this plot that I showed you before, the energy in, ions out plot, and gone back to that same data set and used much more data, and also started to look at correlations, not just with the Poynting flux, but with other quantities that are important for Earth's magnetosphere and the solar wind. And it's not important to understand what each one of these things is physically. The more important thing to know is that there are correlations all over the place. This correlation here may not imply causation. It may be something else going on in the magnetosphere that's causing Earth to respond to the solar wind in this way. Oops, this plot here is a newer version of this plot I showed you before. Poor PowerPoint animation. Okay, so next, another lever that we have, we can compare Venus, Earth, and Mars through observations. But those of you who have met me before know that I do a fair amount of my research on Mars, and that Mars is a really interesting place in terms of magnetic fields and atmospheric escape. It's an incredibly rich place. So let's just focus there for a minute. And I also want to mention this spacecraft again, MAVEN, that's been in orbit since 2014. There is lots of relevant data on every single escape process, on the reservoirs in the upper atmosphere and magnetosphere for escape, on the solar drivers of escape, and on the isotope ratios that tell us about how important escape has been over long periods of time. As a matter of fact, there's so much high quality data that I am going to argue that the best data in the object in the universe about which we know the most with regards to escape is Mars. We know more about escape at Mars than we even do at Earth, and that's the richest data set. So I want to make another point here that focusing on Mars can be beneficial because Mars has a built-in control experiment. Comparing Earth to Venus is fraught with peril because they have different compositions to their atmospheres and are at different distances from the sun. Comparing Venus to Mars is challenging as well because those planets have a different size. But Mars has a nice built-in control experiment where parts of the crust of Mars are magnetized and other parts are not. So there's remnant magnetization in some of the ancient crust of Mars, and this diagram is a map of the radial component of magnetic field. Strong reds mean the magnetic field from the crust is pointing up away from the center of the planet. Strong blues down towards the planet, and white means there's no radial magnetic field. So ups are always connected to downs, and this just shows you that the magnetic field at Mars is complex. There's enough magnetic pressure provided by these regions that you can think of them in a way as small scale umbrellas for the atmosphere, places where the atmosphere might be locally protected from the solar wind on the same planet of the same composition, of the same size, subject to the same conditions as regions that are not protected. So we can compare magnetized and unmagnetized regions on the same object. And here's a very old animation of mine showing that the magnetic configuration at Mars is very complex. There are much better simulations of this these days. So one thing that I've done with the MAVEN data is look to see if the escape rates vary as Mars spins on its axis. Sometimes those crustal fields are facing right into the solar wind. Other times they're on the night side of the planet and not really interacting with the solar wind at all. So if those crustal fields are important, you might expect to see the escape rate from Mars vary as it spins. So what we do is we take our charged particle observations and we draw an imaginary surface above Mars, which you can see in silhouette below this shell of data. And then I use kindergarten skills. I paint by number and fill in each square with the average flux of ions that's leaving the planet. And then I use third grade skills and I add them all up to give me an escape rate. And I can look at that escape rate when the crustal fields are at midnight versus dusk versus noon versus dawn. And there's about 17% variation in the escape rate as Mars spins, but the natural variability from the changing external conditions is much larger than that. So we can only infer that the crustal fields are not very important in controlling escape from Mars, that the magnetic field doesn't matter so much. We're not so comfortable with that result because it's globally integrated. Instead, we'd like to look at escape in a magnetized region and a non-magnetized region. And 3 of us on the team have done that. Turns out me, my postdoc, and my graduate student have all independently done this. And so I took a vote and picked my graduate student to show those results. And he just defended last August. And I'm only going to show you the top left plot here. So this is the flux of molecular oxygen ions away from Mars as a function of altitude and as a function of the strength of the magnetic field beneath that location. So strong crustal fields are over here, unmagnetized regions are over here. And there's definitely a difference between unmagnetized and strongly magnetized regions. And if you want to integrate that flux in each column, the strongly magnetized regions have more escaping oxygen than the unmagnetized regions. This result suggests that on local levels, the magnetic field actually does matter. Okay, now worlds in a box. This is our last maybe lever that we can be using to tackle this question. Let's use simulations. The simulations are fancy. We can put all the physics in. We can control everything. So there's an issue here, however, and one reason that we propose this Team Science Center. Turns out that the community that models Earth, a magnetized planet, has diverged from the community that models unmagnetized planets like Venus and Mars. And the modeling approaches have different physics and different assumptions included. And what we're seeking to do is to zip those communities back together and make all the best choices, combine the best of both types of models into one sort of uber model that can address this question. Where in that model, we can turn the magnetic field on and off or to an arbitrary field strength. So here's an example of the kinds of models, modeling groups that are now working together on this project. You know, several different groups that model unmagnetized planets using different kinds of models and different physical assumptions, and then a group that models magnetized planets like Earth. And we actually have 2 or 3 additional modeling groups not represented on this slide as well, who joined subsequent to us putting the proposal together. So let's talk a little bit about where we are here. One of the first things that happened is a graduate student at UCLA went and mined the literature as well. There are lots of modeling publications over the past decades. What did they tell us about the importance of being Venus, Mars, or Earth? So far, she only has Venus and Mars on her plot. Venus is the triangles. So that's up here, unfortunately colored red, just like some of the Mars as well. So Venus is up here, Mars is all of the X's at different solar conditions. And what you can see if you glaze your eyes is that as the solar wind blows harder, escape increases from Mars. But what you also see is that lots of models have been applied to certain types of conditions, and there's a wide range of answers that those models give back to us. Trusting any one model comes with some risk attached. It's really when the whole modeling, and science isn't a democracy, any one of these X's could be correct, but we certainly have a warmer, fuzzier feeling if we're sort of in this range with our modeling results. So there's work to do here to understand why the different models give us different results. So in my group, we have one of these models as well. We can simulate Mars-like exoplanets with different magnetic fields. And a previous student of mine, Hillary, ran the model 7 different times with the magnetic field shut off at 0 nanotesla, and then different strengths of the magnetic field. And from her modeling results, and this models the solar wind flowing towards the planet and interacting with the planet and its atmosphere. From her results, we can see the configuration of the magnetosphere. What do the magnetic field lines look like in this situation? And for a weak magnetic field, it's like spaghetti noodles draped around a basketball. And as you dial up the strength of the planet field, of the magnetic field coming from the planet, you get more like a angelfish or a jellyfish or something like that configuration, where there's some field lines that connect at both ends to the planet, and you could have charged particles trapped in there, and other field lines where they could escape. So with her model, she looked at the escape in these different conditions. Here, the x-axis is the strength of the magnetic field, and she got a very surprising result. The escape rate from the model has a maximum at an intermediate field strength. And naively, we were expecting to see something that monotonically increases. The stronger the magnetic field is, the more escape you expect, or monotonically decreases. The weaker the magnetic field is, the more escape you get. And as you dial up the magnetic field, it protects the atmosphere more and more. It turns out kind of both are true, and there's a sweet spot that maximizes escape. And I'll caution you here that this planetary magnetic field strength is still a couple orders of magnitude lower than Earth's magnetic field strength. Earth's magnetic field strength is high enough that it really challenges some of these simulations. It causes them to have to reduce their spatial resolution and their time resolution both, and it can bring those models to their knees. That was a surprising and disconcerting result, but it turns out it qualitatively agrees with results from others in our group using different models, where there's a sweet spot that maximizes escape for certain species. And if we had been smart enough, we would have realized that there was work 8 years ago for Earth. This isn't really escape. This is Joule heating, sort of how much energy is being powered in the ionosphere of Earth as a function of the strength of Earth's magnetic field, or an imaginary planet's magnetic field. And this result also showed a maximum in the power that you can impart at intermediate field strengths. So a lot of different groups are converging right now on this surprising result and working together to understand it better. So to wrap up, I have maybe 3 slides on what the future holds. And where we're headed next. So first of all, exoplanets and exoplanetary situations is an obvious application of this kind of work, a place where maybe the results could be useful. And we're just beginning to be able to detect magnetic fields at exoplanets, and Eugenia can tell you a lot about that, and so can Melody as well, and others I'm sure who are on this in this meeting. And then also we're already detecting the escape of atmospheric particles from exoplanets. So I think it's just a matter of time before we're going to have the information we need to do correlations with exoplanets between atmospheric escape and strength of magnetic field. These observations are in hand and becoming pretty straightforward to make in my understanding. These observations are going to take a while to be able to get down to the sizes of planets that I've been talking today. Maybe decades to get down to Earth-size planets, but we'll see. So another thing that I've been noticing in the literature, at least in press releases, is that it is still assumed that Earth-like exoplanets may have magnetic fields capable of protecting life, and that's because they protect the atmosphere from being lost to space. But in the heliophysics and planetary science community, we're seriously questioning this assumption right now and trying to determine whether it's true. And so seeing this in press releases makes me think, aha, I have a contribution that I could make. And at first I think, well, okay, the exoplanet community maybe isn't in as close touch with the planetary science community as I would like. But then you see press releases like this from 2019, that's from the planetary science community, that is making the exact same assumption. Even more embarrassing, this is based on MAVEN data, the mission for which I'm the deputy principal investigator, and it quotes me in the article. And this article claims that because the Martian magnetic field disappeared, the solar wind stripped the atmosphere away. So really, it's a community-wide question where we have to come to an answer and then be able to effectively communicate what that answer is so that we're all on the same page. Finally, what we plan to do within our little happy team of scientists is continue with our approaches and expand. We'll do more apples to apples comparisons of escape at Venus, Earth, and Mars, and at Mars alone as that Rosetta Stone. We're developing a merged model for planetary escape. We're unifying sort of the theoretical and quantitative understanding of how mass and energy flow through magnetospheres. I didn't show you much about that today, maybe not anything. And we're adding other escape processes and other kinds of objects to our work. We want to have a big tent in what we're thinking about. Finally, we will, on some level, fold in studies of radiation environments. And definitely we will fold in atmospheric chemistry as influenced by magnetic fields into our work. We have a collaboration right now that's just starting up with another team, Science Center, that's focused on atmospheric source processes from the interiors of planets and building atmospheres from within. So our two centers are starting to communicate with each other and become an Uber center. So let me stop right there, say that there's lots to do, and I'm really excited to be able to do some of it. And I think maybe what we should do also is vote again, and I'll leave it there.
Great. I will relaunch the poll, and let's see what people say. This is now the post poll. Can you see it, David?
I can see it. It's coming in. We got about 60 votes.
Yep.
So far.
68%, 7%. Yep. And you seem to have flipped the distribution.
Attitudes
It's gone from
have shifted.
2/3, 1/3 to 1/3, 2/3.
Yeah.
More or less.
Oh no, what have I done? We're not done yet. We don't know the answer. But maybe this accurately reflects actually where my own community is on this question right now, where I think there are an increasing number of people who are pretty skeptical.
All right. Well, that was interesting. That was definitely news to me. So we have so the floor is open to questions. Please put your questions in the Q&A, and I'll read them off. And let's please applaud our speaker virtually if we wish. That was really an eye-opening talk. Thank you very much. And you're getting lots of praise in the chat. So Sean, I'm going to butcher his last name, Charnecki, asks, in the D to H ratio plot, why does Mars span an order of magnitude, but Earth is shown by a single point? Is this real?
Yeah, I'm not. Actually, there are other people in this colloquium right now who are better situated to answer the question, but I'll go out on a limb and say, no, at different places on Earth, you're also going to get a range of values. But I think what I've heard is that the wide range of values on Mars is making it hard to sort of understand what the overall escape has been from Mars. You know, if you examine different parts of Mars, it's hard to know which one to pay attention to. So when Genda made this figure, they put basically all of the information there.
Jim Lyons has his hand up, so I'm going to activate his mic. Jim, you are able to talk.
Okay, can you hear me?
Yes.
Yep.
Thanks, Dave. That was a truly interesting, fantastic talk. Two quick questions. Is the oxygen ion escape, this is a question about Mars, is the escaping species for oxygen for Mars primarily the O+ ion, or is it O neutral? And do we know? And I have a second question, which is similar, but it's for Earth. And that is there any return flux from the magnetosphere of oxygen ions to Earth's atmosphere?
Great. Both the questions are great questions. So for Mars, dominant escape today is photochemical escape of oxygen by maybe a factor of 5 or so in excess of the ion loss. So the photochemical escape is the escape of neutral oxygen, not oxygen ions. And this was a bit of a surprise that came back from MAVEN. We were expecting ion loss to be dominant there. That doesn't mean that photochemical escape has been dominant over history. And the photochemical escape requires recombination at some point. So it requires that those O2 particles that become photodissociated start as ions. And so there's a potential role for the magnetic field to play even in the photochemical escape process as well there. But yeah, neutral escape is dominant for oxygen. An additional thing that you didn't ask, but I'm going to pretend that you did because maybe you were thinking it, is where did that oxygen come from in the first place? We have this conundrum where it could have come from water, but it also could have come from the dominant species in the atmosphere, carbon dioxide. And so we can't really untangle that with oxygen measurements alone. We need hydrogen and carbon measurements to go with them. And we have some constraints on hydrogen from MAVEN, some pretty good ones, but we were just beginning to get the constraints on carbon to find out where the oxygen ultimately came from. Your second question was about Earth, and I was really excited about it, and I forgot it.
Can you still hear me?
Yes.
Okay,
Yes.
good. Actually, I didn't know I was on. Yes, I was just wondering if there is a return flux of oxygen ions from the magnetosphere to Earth's atmosphere. In polar regions, presumably, but maybe even lower latitudes.
Yeah, great question. So at lower latitudes, yes, definitely. A lot of that plasma ultimately goes along the magnetic field line and just comes straight back into the atmosphere at the conjugate foot point of the magnetic field line. And even for the oxygen, the ion outflow in the cusp regions, some members of the terrestrial community think that almost all of that is escaping. Other members think that it's 50% of that upflow that is escaping, plus or minus 50%. So that's, his name's Bob Strangeway at UCLA, someone who I really trust. And Bob says 50% plus or minus 50%, which basically means we don't know how much of it actually leaves the system entirely.
Okay, thank you very much.
Yeah.
Thanks, Jim. Okay, Steve Semkin asks, do magnetic field reversals have an influence on escape processes? This comes from a geologist.
I think so, but several years ago, I was thinking of writing an RNA proposal to look into this, and I looked to see how much literature exists. There's hardly any. I think there's one space physicist in our field, Karl-Heinz Glassmeyer, maybe, I forget who it was, someone from Austria who's written a paper or two on this, but not a lot. So I can speculate for you and think that it should influence escape, but that we don't need to be worried. So during a magnetic reversal, as you know, Earth's field changes from having most of the power in the dipole terms to putting that power into higher multiple terms. What that means is the magnetic field kind of reorganizes and shrinks, and then it flips over, and then it goes back out again to the dipole. So it's a reorganization, a flip, and then a growing out again. During the reorganization, the magnetic field can probably, the magnetosphere can probably shrink down to even below the top of the atmosphere, making Earth look a lot like Venus or Mars in terms of its interaction. The homing pigeons are gonna hate it. Aurora watchers are gonna love it. There can be aurora all over the place. And some of these escape processes driven by the solar wind may be enhanced at that time, effectively in the absence of a magnetic field. It remains to be seen. But the time scale over which these reversals happen is short compared to the time scale over which the time scale that we think is required to substantially change atmospheric abundances. I think the stronger effect would be on power grids and surface systems, on biological systems that navigate using the magnetic field, and on atmospheric chemistry. There could be important consequences there as well for a period of a century or something like that. So there's definitely some interesting science to be done, and I don't know who's done it.
All right. In the interest of time, we'll ask one more question. We have a bunch more. We'll ask just one more. This is from one of our geobiology faculty. Elizabeth Trembeth-Reichert asks, how do these findings apply to water world or icy moon astrobiology targets? When we talk about habitability.
Yeah, let's start with icy moon, because I think the application there is fairly minimal. You know, there could be some important consequences of magnetic fields for worlds with subsurface oceans, but in terms of escape of an atmosphere that makes, you know, something stay liquid on the surface, that's not a relevant topic at all. And even then, the magnetic fields that exist in ocean worlds are often generated by currents in the oceans themselves. So it's hard to imagine, you know, getting an ocean world that doesn't have some sort of salty ocean generating currents. So I think there's not a lot to talk about there, or if there is, I haven't thought of it yet. For a water world situation, I think all of this is still relevant. You know, if you have a water world, you're still going to have some sort of atmosphere above it, and all the escape processes are still possible, and that world could still perhaps have a magnetic field. So I think this is still an important topic there.
If we could identify water worlds, if you knew from observational evidence that you've got a water world, that might tell you something about the question, help answer your question, right? If you also had magnetic field information, right?
Yeah, there's this naive assumption that we have a lot of data in the solar system. We're going to solve the question there and then apply it to say which exoplanets we should look at. But I think it's equally likely that we'll use the large statistics coming from exoplanets to help us understand the problem as well. And that's where there's really great synergy.
All right, if we find that all water worlds have magnetic fields, for example, then one might conclude magnetic fields matter.
Right. And by the way, the answer to the poll question, you know, I was hard pressed to pick a response there. I think the answer is it depends. You know, a magnetized comet and a magnetized Jupiter, I think those are very different regimes that you're in. And I think there are certain kinds of worlds for which the magnetic field is going to be incredibly important for whether it retained an atmosphere. And there are other kinds of worlds for which it's going to be pretty irrelevant.
All right. So thank you very much. That was a wonderful talk. So everybody, please thank our speaker again. And Dave, we look forward to getting you here in person at some point.
Great. Thank you for having me. And I would love to come visit and come see me in Boulder.
Thank you so much, David. That was amazing.
Thank you.
Thanks.
Oh, and David.